Good afternoon, Physics 20. I hope you guys are all doing well today. Ready to rock some physics on this fine Monday? Awesome. So today, ladies and gentlemen, we're going to be looking at a very important topic here. Now, gravitational fields themselves aren't coming up in Physics 30, but we're going to be looking at electric fields and we're going to be looking at magnetic fields and the interaction between the two of them in Physics 30. And the skills and ideas that we develop in this video, as well as the previous video, are going to be coming up next year. All right? Okay. So, ladies and gentlemen, enjoy the meme. Anti-gravity, impossible to put down. Yeah, had to happen. Love it. All right. So, ladies and gentlemen, you guys ready to begin? Awesome. So, ladies and gentlemen, let's begin with some definitions here. So, please recall a force is defined as a push or a pull on an object. So, how can two masses exert an attractive force, so an attractive push or a pull, such as gravity, without being in contact? It doesn't seem to make any sense, now does it? So that's where the idea of fields comes in. So it's a way to describe how a force can be exerted without any physical contact. So in this case, it is a field. These are essentially described as an action at a distance. Okay, so gravitational forces are due to gravitational fields. Okay, so the ability to have an action at a distance. So, ladies and gentlemen, gravitational fields are vectors. They are vectors. They've got direction. Okay, and they have a very specific direction. Okay, now because gravitational fields are attractive forces, that means the gravitational field must be directed towards or into a mass. So, as we see in the diagram here, these are our vector arrows. Now, each of these arrows represents the gravitational field. Now, the arrow, as in all vectors, is pointing towards the direction it's going. Now, notice these field lines here, ladies and gentlemen. Now, these field lines closer to the planet are closer to each other. These field lines up here are farther apart from each other. So remember, ladies and gentlemen, how when we looked at our Fg is gm1 m2 over r squared, remember this guy? Well, remember that our force of gravity is proportionate to the inverse of the square of the radius. So what that tells us is that the farther away we go, the less the gravitational force is. We can also assume, as we'll be looking at our equation down there, that our gravitational field is proportional to the inverse of the square of the radius as well. So the farther away you go, if I extend these vector lines, I can't draw a straight line on here. Sorry, guys. No ruler. So when we look between here, they're quite far apart now. So the farther and farther away you get, the weaker the gravitational field. Makes sense, right? Based on everything we've been looking at so far. Okay. So, ladies and gentlemen, please recall every mass has its own gravitational field. Okay? So, because we ourselves are masses, and because gravitational fields are attractive fields, are we all attractive? Absolutely. Okay. So, ladies and gentlemen, gravitational fields, they extend out essentially infinitely. However, because they become so weak as the radius continues, there gets a point where they become negligible. They become not even worth calculating anymore. And sometimes when the masses are super small, the gravitational fields themselves are negligible. Okay. All right. So, ladies and gentlemen, let's look at our equation. So we've got G. Okay, here's G is equal to either FG over M1 or G is equal to GM2 over R squared. Now, these equations you can find on your lovely data sheets, which are right here. Okay, you guys see them? Right there? Right there? Okay, you don't have to memorize them. All right, there. It's right there. Okay. So, ladies and gentlemen, G is our gravitational field strength or the acceleration due to gravity. I don't care what units you use, newtons per kilogram or meters per second squared, potato, potato. We can do some unit analysis to actually prove that they are the same. We'll do that later. Okay, so Fg is our force of gravity or the weight. Okay, remember that force of gravity is equal to the weight. M1, so that's this mass here, is the mass of an object inside the existing gravitational field. So in that case, it'd be us sauntering along the surface of the Earth. We are inside that Earth's gravitational field. Okay, units, kilograms. M2, which is this guy here, is the mass of the object creating the gravitational field. So this equation is really only useful in a limited number of scenarios where you either A, know G, or know an object's weight. Okay, the mass is generally going to be a given. Now, in this case, this M2, this equation is actually more useful because you can use it in more scenarios. And you can, this is the big G is a constant. M2, say mass of Earth, that can often be a constant because we generally will be dealing with Earth. And mathematically, the masses of all of the planets in the solar system are known. And the radius, that can also be calculated. So this is a much more versatile equation. Now, R, once again, is the radius, the distance from the center of the object to a point in space. So we're not talking about a mass anymore here, or we're talking about any point in space, okay? And G on your data sheet, that's a constant, same as in our last video, ladies and gentlemen. So you'll find that value right there on the back of your data sheet, okay? Right there. And then you have the radius of the Earth and the mass of Earth all right there. Okay. So as soon as you go beneath the mass of Earth, the rest of this stuff, that's all going to be for Physics 30 for next year. Okay. Ladies and gentlemen, you guys are ready to rock? Of course you are. Ready to rock. Ready to roll. Okay, your favorite graphing, as always. Okay, so sketch the shape of the following graph. So identify your axes. So we've got G and we have R. Okay, so if we're going to remember our rules for sketching the shape of a graph, we're going to be comparing the gravitational field strength and the radius. So you're remembering your rule is to write your equation so that way it lines up with your y equals mx plus b. And in order to do that, you have to have whatever is on the y-axis isolated on its own. So in this case, it's already done for us. So our g times the mass of the object, creating the field, divided by the radius squared. Well, we're going to make our mass constant, and this is a constant. So we can exchange that equal sign for our proportionate, make these 1. So G is proportionate to 1 over R squared. So G is directly proportionate to the inverse of the radius squared, or G is inversely proportionate to the square of the radius. So you can word it however, which any of those ways you want. So now, ladies and gentlemen, this is similar to, whoopsie, let's erase that. That's a random G. It was supposed to be a Y, but so much for that. There we go. Whereas Y is equal to 1 over X squared. So because of that, then we can draw our graph like this. Okay, it should be going actually a little bit lower, closer to that X axis there. There we go. That's better. Sounds good? All right. So, ladies and gentlemen, our lovely graph. It's beautiful. Okay. So what we've got, calculate the mass. So m is equal to 3.5 times 10 to the kilogram. So a mass of 350 kilograms has a weight. Now remember, ladies and gentlemen, weight is Fg. Random F that has followed us down from the previous section. So our Fg is 9.6 times 10 to the 3 newtons. Is at some location out in space. Where? Doesn't matter. Calculate the gravitational field strength at this location in space. Okay, so we've been asked to calculate G. So, well, guess what? We've got mass and we've got the weight. So because we have these two values, we can use this equation. Okay, so we take our Fg, which is our 9.6 times 10 to the power of 3 newtons. That's supposed to be an N. There we go. Newtons. And we then divide that by our mass, 3.5 times 10 to the power of 2 kilograms. And we're going to get the lovely value 27.4285 ... You can either use newtons per kilogram, or meters per second squared. Makes sense, right? All right. So, ladies and gentlemen, we now sig digs units. 3 sig digs, 3 sig digs. So I do my appropriate rounding and I wind up with 27.4 meters per second squared or newtons per kilogram. I don't care which one you use. As long as you use either of the two, you're good. Okay. So, any questions? Right. We're on YouTube or Google, Google Classroom. So if you have questions, sign up on Google Meet. All right. Got so used to teaching in class. We can actually answer your questions right then and there. I'm looking forward to being back at the classroom. I miss you guys. All right. Ladies and gentlemen, at what distance from the Earth's surface is the acceleration due to gravity 7.33 meters per second squared? Okay. Well, we have been given G at 7.33 meters per second squared. We are definitely not on the Earth anymore. We're in space, if that is what Earth's gravitational field is. So we have Earth. The second you see the word Earth, that means you have two constants that you can get from the back of your data sheet. You can get Earth's mass and you can get Earth's radius, both of which you're going to need. Okay? So from your data sheet, you can see that the mass of Earth is the lovely value of 5.97 times 10 to the power of 24 kilograms. We know that the radius of Earth is equal to 6.35 times 10 to the 6 meters. Now, you have been asked to calculate what is the distance from the Earth's surface. Okay, so what we're going to have to do for this case, here is the radius of Earth. I'll switch to blue. Okay, there's the radius from the Earth's surface. Here is dude in space. Now that dude is in space, he is above the Earth's surface. Okay, the value that you have been asked to calculate is this value here. Okay, however, when we go and look at our equation here of G equals GM2 over R squared, well, ladies and gentlemen, this radius here, this R squared, is going to give you the value from here all the way down to Earth's surface. So that is this light blue line is what this guy here is. So that means calculate this, subtract this, which is this, and then it will give us this, which is what we want. Oops, that should be dark blue. Okay, this is the value we want. So this minus this will give you the value you want. Cool beans? Cool beans. All right. So, ladies and gentlemen, let's calculate our radius. So we're going to rearrange our equation. You're going to divide by little g. You're going to multiply by r squared. And you're going to wind up with r squared is equal to g times the mass of the Earth divided by your little g. We are now going to square root both sides. And our radius is equal to gm over g square root. Plunk in your numbers. And big G, data sheet, ladies and gentlemen, 6.67 times 10 to the power of negative 11. You're going to multiply that by the mass of Earth, which you get from your data sheet. So 5.97 times 10 to the power of 24 kilograms. Divide by G. Please don't use 9.81. If you use 9.81, I will cry inside. It's not 9.81. We're not on the surface of Earth anymore. We're out in space. 7.33. Okay. Square root the lot. And we're going to get the radius t. I'm going to say radius t for radius total because why not? Okay, so our total radius is our 7.3705 ... times 10 to the power of 6 meters. Now remember, as I mentioned earlier, our radius total is equal to our radius of Earth, there we go, plus we'll call it, say, radius from the surface. Okay. This radius from the surface, that's what we want. So we are going to have to take our radius total and subtract the radius of Earth. Okay. So the radius of our from the surface, which is what we want. So from here to here, okay, that is going to be our radius total. So what we calculated here, use all digits, please. No rounding yet. So 7.3705 ... times 10 to the power of negative 6, positive 6, minus your radius of Earth, which is 6.35 times 10 to the power of 6 meters. So our radius, how far we are from the surface of the Earth, is equal to, ladies and gentlemen, once you put it into your calculator, 1.000519 ... times 10 to the power of 6 meters. Now, sig digs, units, I want 3, please. Our constants all have 3 sig digs. So the radius from the surface, so the distance from the surface of the Earth to where the dude is in space is going to be 1.00 times 10 to the power of 6 meters. Sounds good, guys? All right. So, ladies and gentlemen, on to the next one. Okay, this is a fun one. You guys love these, right? No, you guys probably are going to complain about this one. It's fun. These questions are fun. Math wizardry, ladies and gentlemen. Oh, yeah. So we're going to be using some ratios. Ratio substitution and our lovely... What's the term I'm looking for? I'm looking for factoring. There we go. That's the word I want. So, ladies and gentlemen, the gravitational field strength produced by a mass at a particular distance, so we don't have the mass, we don't have the radius, is 6.44 newtons per kilogram. Okay, so here is our original. Okay. We have our G is 6.44 newtons per kilogram. Now remember, ladies and gentlemen, that G is also equal to Gm over R squared. Okay, which means 6.44 newtons per kilogram is also equal to G. That's a 6. There we go. It's also equal to Gm over R squared. Okay, so that's our original setup. Now, because we're going to be increasing the mass by a factor of 4, and we are going to be reducing the distance to a third of what it was, we are going to have a change in our gravitational field. So we are going to be modifying. This would be spelling modified wrong. There should be an I. There we go. Spelling is not my thing, ladies and gentlemen, as you guys know. So what this tells us is that we have a lovely value of our m prime is equal to 4m, and our radius prime, so our modified radius, is either equal to 1/3 r or r over 3. Okay, doesn't really matter which one you use, your results are going to be the same. Okay, so I need to find out what G prime is. Remember that prime means is our thing we're using for modified, and something we're going to be using a lot next year. Okay. All right. So our G prime, what we're trying to find. So I have my G prime is going to be equal to Gm prime over R prime. I am now going to substitute 4m for m prime. Okay. Now, I forgot to square my radius. There we go. So r prime squared. So I'm going to take my r prime and I am going to put in 1/3 r squared. Okay. So my next step, ladies and gentlemen, is I am going to have to do some squaring. So please remember that when you're going to be squaring this, we're squaring both 1/3 and we're squaring r. Okay, so G prime is equal to G times 4m divided by, now 1 squared is 1, 3 squared is 9. So 1 over 9 r squared, because r squared is r squared. Okay, now what I can do is, well, I'm going to look at this 9. This 9 is under 2 dividing lines. When a number is underneath 2 dividing lines, really it's on the top. Okay, so when I'm going to factor this out, I'm going to Gm over r squared. So I'm going to factor that out, multiply that. 4 is on the top, factor out my 4. I'm going to factor over 1 over 1 over 9, which really means I'm going to factor out 9. Okay, so ladies and gentlemen, I'm going to factor out 4 times 9. So G prime is equal to Gm over r squared times 36. Okay, so my gravitational field strength is going to be 36 times what it was. Nuts, eh? Remember from previously, this value here, Gm over r squared, is equal to 6.44. So 6.44 newtons per kilogram times 36. Your G prime, ladies and gentlemen, is going to be 231.84 newtons per kilogram. Okay, so ladies and gentlemen, sig digs, units, as always. Okay, so ladies and gentlemen, 3 sig digs, that's going to round up to 32 newtons per kilogram. There you are. All right, ladies and gentlemen, there's your answer. Those are fun. Highly enjoyable. Okay, so I've got here for you guys is another question. Okay, last one, I promise. Now, this particular question here, ladies and gentlemen, mass 1 is 172 kilograms. And mass 2 is 163 kilograms. Okay. I just need you guys to hold on for 1 sec. I got to pause the recording and I will be right back. Hold your horses. All right. I'm back. This is where you guys say I'm Beethoven. Yeah. You guys getting sick of that pun? Maybe? All right. So ladies and gentlemen, we have our two masses and we've got our two radii here. And we need to determine what the gravitational field strength at point P is. Now, this is something that is going to come up, this idea is going to come up next year in Physics 30 with electric fields and magnetic fields. So be aware of that one. So this is an important skill. So ladies and gentlemen, point P is essentially just that random point. Because remember, gravitational fields are the strength of a field at a certain distance from a mass. Also remember that gravitational fields are always attractive. Okay? So that means that I'm going to make this gravitational field strength 1. Its direction's going that way towards that mass. I'm going to make this G2 for object 2. Well, it's pulling towards that mass. So point P is going to be experiencing two different forces. It's going to be experiencing G2 and G1 in opposite directions. Okay? So the same way, because these are vector fields, we can add them the same way we would add any vector, which is awesome. And we're back. Please excuse the lovely technical difficulties. That's what we do every day. Okay, so ladies and gentlemen, we left off with having our masses labeled. This guy here, our mass 1, is 172 kilograms. We left off with this mass being 163 kilograms. We left off explaining how, because gravity is an attractive field, that means G1, we'll call it G1 because it's mass number 1, is going to be pointing towards the mass. G2 is going to be going in the direction towards the mass. So that means point P is going to be experiencing two fields this way. Okay? Now, because it's a vector, we can add these vectors the same way we do all of our other vectors. Okay. So, ladies and gentlemen, we're going to calculate G1, okay? So, recall our equation, Gm over r squared is going to now equal 6.67 times 10 to the power of negative 11, and multiply by our mass of 172 kilograms, divide by our radius of 27 squared. Don't forget to square your radius. And we're going to wind up with a gravitational field at point P from G1 alone of 1.5737 ... times 10 to the negative 11 newtons per kilogram. Okay. So, ladies and gentlemen, G2, Gm over r squared, big G, always the same, M2, 163, divide by our radius of 15 meters squared. Don't forget to square your radius. And then we wind up, once plonked into your calculators correctly, 1.832 times 10 to the power of negative 11 newtons per kilogram. Try not to write on my face. All right. So, I'm going to scroll down. So now we have our two gravitational fields. So what we need is to find that net vector, that gravitational field net. Well, just like we would have a force net, we can have a field net equation. So let's look at these values and let's make the bigger one positive, just because it's easier. Well, G2 is bigger, so I'm going to make our G net is going to equal to G2 plus negative G1. Why is G1 negative, ladies and gentlemen? It's going in the opposite direction of G2. Okay, and we chose to make G2 positive because it's larger. Okay, so that means right is going to be our positive direction and left is going to be our negative. So my G net at point P, which is going to be experiencing both fields, is going to be I'm actually going to write this down. So right will be positive, left will be negative. Okay. Remind me someday. I'll tell you guys why I always have to circle my positives and negatives. Okay, I'll tell you guys someday. Goes back to university with a chem class. All right, so ladies and gentlemen, 4.832 times 10 to the power of negative 11. Always use all digits here in your calculator. Don't round here, only round at the last step. And we're going to subtract that from our 1.57 times 10 to the power of negative 11. All digits in your calculator, no rounding here. And our G net is going to wind up as a positive value. And we get 3.258 ... times 10 to the power of negative 11 newtons per kilogram. All right, time for sig digs in units before I deduct myself half a point. And I also don't have my direction here. I would lose a whole point on that one. Goodness. Can't have that now, can we? So sig digs rounding units. I want 3 sig digs, so that's going to round upwards. So 3.26 times 10 to the power of negative 11 newtons per kilogram. And I wound up with a positive number, and the positive number is to the right. So my direction is right. All right, ladies and gentlemen, pun intended. That is it for this video. Please excuse the technical difficulties. We've got a bunch of practice problems for you guys here. I recommend doing some of these ones. Give them a try. This is going to be an important topic for both your assignment, and if there was a unit test, I would say on test. And it will be an important skill for next year. Alrighty-o. And I've also given you guys some more practice problems for you guys to work on. Now, for this guy, for number 7, I'm going to give you guys a tip. For that one, what I would do is Pythagoras, the same way you would add any other vectors. All right? Okay. So, ladies and gentlemen, I hope you guys all have a good rest of your day. No fires, injuries, or explosions. Talk to you guys later. Bye. Now I can't turn it off. There we go. Bye. And I'm back again, ladies and gentlemen. So just kidding that we were done this video. One thing I said we were going to do, but forgot that I said I was going to do it. Now I have to come back and do it again, is the unit analysis to prove that the newtons per kilogram unit is actually equal to meters per second squared. So, ladies and gentlemen, let us do that now. So in order to prove this, we first need to break down what a newton is. Because remember, a newton is actually a combined unit. It's an acknowledgement to Sir Isaac Newton. Now, remember, ladies and gentlemen, that our force is equal to mass times acceleration. Remember that force is the unit in newtons. So we have, I'm not going to rewrite this equation using units. So a newton is equal to, now mass is always in kilograms, and we're multiplying, and acceleration is in meters per second squared. So a newton is a kilogram meter per second squared. So I'm going to take this value and I'm going to plonk it in place of that newton. So a kilogram times meter per second squared, which is a newton, per kilogram, and then I'm going to leave that meters per second squared. Well, look at this, ladies and gentlemen. Kilograms. We've got a kilogram divided by a kilogram. They cancel. So I am left with meters per second squared equaling meters per second squared. So they are absolutely identical. They mean the exact same thing. So you guys are welcome to use either newtons per kilogram or meters per second squared because they're the same thing. Isn't that exciting? I say it's exciting. Okay, now the video is really over. I hope you guys have a good rest of your day, and we will see you guys next time. No fires, injuries, or explosions, please. See you later.